Dear participant, welcome back to our ongoing workshop. It gives me immense pleasure to welcome you to the day 9 of our faculty development program. Today's theme is Inferential Statistics, Part 2 and Regression, Correlation Analysis and Simple Multiple Regression Applications in Business Forecasting using R programming. In the first session, we built a solid foundation in descriptive and inferential statistics. Today, we take the next important step, exploring correlation and regression, which are the powerful tool for understanding relationship between variables and predicting future outcomes. Regression techniques from the backbone of the modern business forecasting and decision making, and with the help of our software, we will not only learn the concept but also see their real time application. So once again, welcome to all the participants and welcome dear professor for this valuable session. And now we can start the session. Over to you, dear Professor Harmanpreet Singh Kapoor.
Okay, thank you, sir. Thank you, sir. So basically, so if someone has any doubt regarding the yesterday session, one can ask me 1-2 minutes. Otherwise, I will start the today's session. So if there is no doubt, then we will continue with today's talk. Then later on, if you want to have, if you have any question later on, you can ask those questions later also, right? Okay, I think my screen is visible to all of you.
Yes, sir. Perfect.
Yeah, okay, fine. So before going to start the session, so there are two basic things that most of the persons, they may be, they are confused that what we are going to cover today. So yesterday one has asked me that can you cover cross-sectional studies and time series studies or latitude studies, right? There is, ma'am, are you there? So you have asked me these questions yesterday. Longitudinal studies, right? So they be longitudinal studies, right? So someone has asked us that whether what type of studies we are going to cover. So we are first going to discuss the basic things. Then I'm going to emphasize that which part we will cover under this segment. So today we are going to cover a very important thing, and maybe all of you are very much familiar with the word that is called covariance. Can anybody tell me what's the meaning of covariance? There is another term that is called correlation. And maybe you have heard about correlation more as compared to covariance. Is there anyone that can explain the meaning of correlation as per your understanding? Then I will explain to you that whether you are on the right track or not. My voice is clear, right? Hello. Hello. Can you hear me? Hello. Can you hear me?
Yes, sir. Audible, sir.
Okay. So can anyone explain me what's the meaning of correlation as per your layman understanding? Or maybe we have heard about this term regression. So can anyone can give me some basic understanding about these three terms so that I can get to know whether we are on the same page or not? Okay. I think no one is responding, so let me take this privilege to explain this because now, so let us suppose we have two variables. So I'm taking not x and y, I'm taking height and weight. Why I'm considering them as a variable? Because when we observe the height of different persons, so variable means that the value of that thing that varies for different persons. That's why it is called variable. Right. So height is my one variable, weight is on my one another variable, and I want to see that whether there is any connection or there is some relationship between these two variables, height and weight. So to observe this thing, so covariance is the first component that helps you understand that whether there is some connection between these two variables or not. Okay. And we are talking about only the linear relationship between these two variables. That is very important point you have to keep in mind. So whenever we use these measures like covariance, correlation, regression, our main objective is to understand that we want to study the linear relationship first. There are nonlinear regression models also available in the future, but we stick for today's session, we stick to only linear relationship. Okay, so what's the meaning of linear? So linear relationship means that so when we plot one variable value on the x-axis value and another variable value on the y-axis value, if we draw a straight line, and most of the time we found that whatever the corresponding value, that means for one first person, we got height as 5 feet. It can be written as 135 centimeter, 165 centimeter, and weight as 70 or 60. For the second observation, second person, I got height as 155 centimeter and weight as 70, and so on. So if I'm going to plot this value of height on the x-axis, and I'm going to plot the value of weight on the y-axis. So while plotting these together, that means 135, see somewhere if I start with 120 and I go to 170, right? And weight I'm going to start with the 50 and go to 100. The minimum value I have observed as 50 and the maximum value I have observed as 100, or it can be 120 also. So while plotting this value together, that means if I consider this as 135, for example, here somewhere, and corresponding to weight is 60. So somewhere here I got my first point, and 155 should lie here something, and corresponding to 70 lies something close to this side. So now you can see that by you can say plotting these points on the chart, that chart is called scatter plot. Okay, by plotting these points on the chart, if all the points lie on a straight line, there may be possibility that some point can be here, some point can be here, some point can be here. But if you find most of the points close to the straight line, that is 45-degree line. So if most of the points close to this line, then we can say that these two variables, they are highly linearly correlated to each other. The definition is clear. It means that there must be some relationship exist between these two variables. My voice is not clear. I'm speaking very close to the mic. My voice is clear or not? Tell me. Hello. Can anybody respond whether my voice is audible or not? Okay, thank you. So basically, what I'm trying to say that while making this scatter plot, and I'm taking the point of height on the x-axis and the point of y on this weight on the y-axis, while putting them together. So if most of the points lie on a straight line, then I can say that these two variables, they are linearly related to each other, right? So so covariance will tell you that whether there's any relationship exists between two variables or not. So we found that if I consider height and weight covariance, so if it is coming to be zero, I'm not going to discuss the mathematical formula for covariance because it is not required. But for your understanding, I can say that if the assumption that all the data set should be of this bell-shaped type of curve, and we got covariance is equal to zero, then it means that there is no relationship exists between this height and weight variable. But if it is not coming to equal to zero, it can be greater than zero, it can be less than zero, right? So in that case, we can say that there is some linear relationship exists, linear, non-linear. It can be anything, but I'm emphasizing that there is some any relationship exists between these two variables, right? So now to get it more relevant for you for understanding, we have that means some of the researchers, some of the you can say statistician, mathematicians, they have derived a formula that is for correlation. Formula or technique, you can say. So, and the beauty of this correlation method is that correlation technique is that the value lies in the range of 0 to -1 to 1. Okay. So what is the meaning of this thing? So if the correlation coefficient that is represented by either rho or most of the books are R, so if it is equal to 0, that means that there is no linear relationship exists between this variable height and width. If rho is equal to +1, it shows that height and weight they are positive linear related, strongly positively related. That means what's the meaning of this thing? It means that if you increase the value of height, the value of weight automatically increase in this case. Okay, positive relationship. And if the this correlation coefficient is equal to -1, it means that if height increase, weight decrease. If height decrease, weight increase. Although we know that height and weight they are very strongly correlated to each other, and most of the time we have observed that when height increase, weight also increase. So this method, this possibility is not valid for the example of height and weight, but this is just a representation that what's the meaning of correlation coefficient when we have this negative value. So it means that one variable, if the value of one variable increase, the value of the variable decrease, and vice versa, and so on, right? So this concept is clear, right? Are you with me? Okay. So now I think all of you have still considered this thing that they have not observed or they have not heard about that in literature. Do not just calculate the magnitude value of the correlation coefficient linear relationship. We also test that whether our correlation coefficient is significant or not. This thing is very much new for all of you. This, we have to keep this thing in mind that till now what we have derived, we have discussed that whether correlation is equal to 0, it is equal to +1, or it is equal to -1. But now we will study further that whether that is there any significance of this correlation coefficient or not. Significance means whatever the correlation we derive, that is either it can be close to +1 or either it can be close to -1, whether that can be proved statistically or not. Because this is a mathematical formula that only gives you a value whether it is close to 0, it is close to +1, or it is close to -1. But from the point of statistical thing, whether we can say that the bond is very strong. So to do that, we use this criteria that we will test this rho equal to 0, so it not equal to 0, and alternate possibilities can be rho is greater than 0, rho is less than 0. So now I'm going to give emphasize some assumptions that under the assumptions we can check this test. The assumption is that our data set should follow normal distribution. This is the first requirement. And the distribution of the correlation coefficient, right? So I use a notation T that is a test statistics function that will be used to test this null hypothesis and nullity hypothesis. And from the literature, it is proved that it follows T distribution with n-2 degree of freedom. Okay. So if someone has any question in your mind that why we consider n-2, why we not consider n-1? Is there anyone this question in your mind that why we have not n-1, why we have n-2?
Yes, sir.
Okay, because the reason is that we whatever the mathematical form that we will use, that was r square root of 1 minus r square multiplied with square root of n-2. Okay, that will consist of estimation of two parameters. Okay, so what are the parameters? Once we are estimating rho with small r, so we are also have this assumption that our normal distribution that has mean 0 and various sigma square, but sigma square is unknown. So we are estimating sigma square with estimator function s square. So one loss due to this estimation of parameter sigma square, and another we are estimating rho from the sample observation that is R. That's why we have two loss of degree. So we have this n-2 degree in that. Maybe this is a very you can say initial thing, or you can say in the layman language I have explained to you. But if someone will go for the derivation of this function, then one can easily see that we have to reduce 2 degree of freedom from the total number of sample size. Then only you can see the mathematical expression that it follow T distribution with n-2 degree of freedom. And one thing you have to keep in mind, as you are directly following some softwares, So you do not have to remember that what's the degree freedom for this test, for this test. But when you are going to solve this manually, although this thing is not valid for today's scenario, because nowadays a lot of softwares are available, but still think about that. Why sometimes we have n minus one, sometimes we have 2 degree of freedom. Like yesterday, someone has asked me that for F test, we do not have this n1 plus n2 minus 2. So in that case, we have 2 degree of freedom. That is for this is for numerator degree of freedom, this is for denominator degree. Because the distribution functions, that means like F distribution function, that is defined in such a manner that they need 2 degree of freedom. T distribution that is defined in such a manner that only 1 degree of freedom. Similarly, chi-square distribution is there. Okay, so basic idea is that we have to go with the three critical things that is already exist in the literature. But if someone is more keen that how they have done that, the complete derivation is available in the literature. So one can refer that. Okay, so for the simple understanding that here we will have n minus 2 in spite of n minus 1 because we are simultaneously estimating 2 parameters. One is for rho and second one is for sigma square. That's why we reduce to degree, right? So now what we will conclude. So let us suppose if we again emphasize that we assume alpha as 5%. Okay. And from the test 6, we got p-value less than 0.05. So what we do? We reject the null hypothesis. And what's the meaning of null hypothesis? That there is no linear relationship exists between these two variables. But when we reject the null hypothesis, what will happen? So now we have to statistically that the variable height and weight, they are linearly strongly related to each other from the statistical point of view also. That means if you try to construct any, you can say regression equation over these two variables, you can construct that. So can you answer me that which variable should I think that consider as a dependent variable and which variable should I think that it can be work as independent? Any idea from the audience? My question is clear because I have just tell you that from the correlation coefficient, I got some idea that these two variables are strongly with each other. Now, my next question is how to construct the regression equation.
So height will be the independent variable. Weight will depend on height.
Okay. Any other guesses? Hello.
Price is a function of demand, we can say. The price is the independent variable, demand is the dependent variable.
So in this scenario, I'm talking about. I know that demand and supply is another thing that we can think about from the economic point of view. But in this scenario, so which variable you think that we should consider height as a dependent variable or independent? So ma'am has suggested that we should consider height as independent variable and the weight as a dependent variable. Okay, the answer is that in most of the scenarios, we observe that when the person height is more, right? So the weight is automatically high, right? So in that scenario, the ma'am assumption is correct. That means if the person height it means it keeps on increasing, automatically the weight will increase. But in other cases also, there is no strong relationship exists between considering height as a independent. Sometimes we consider height as a dependent also, but that is some special cases, not for the other. Okay, so weight will increase in those persons. So sometimes it is possible that the person whose height is 5.5, that weight is also 110 kg. Okay, so generally the assumption is right. The ma'am has correctly said that height can be considered as independent and weight can be considered as dependent. But in other cases, one also has to cross check that if you take the vice versa case, then what will happen? Okay. So the idea is clear. So now let me go further. So we have discussed till now that one variable can work as a dependent variable, one another variable can work as an independent variable. So because we are talking about simple linear regression till now, simple linear regression. So what's the meaning of this term? Simple. Simple means where we have considered only one independent variable and one dependent variable. Okay, so if I consider weight as my dependent variable, height as my independent variable. So now I think we have observed that there are some coefficients terms in the literature like beta naught plus beta 1 into something plus height plus error term. So what are these terms? Can anybody explain me? Or you have, I think, have seen this equation in any other book if you start reading the equation term. Or y is equal to beta naught plus beta 1 x plus epsilon. Maybe some of these books may be neglected as epsilon term. They have only written y is equal to beta naught plus beta 1 x. Anyone can help me that what's the meaning of these equations?
It means the independent variable has a linear relationship with the y. Means linear relationship with the x and y.
Okay.
With some intercept, which is intercept is beta naught, and with
Yeah.
slope beta 1.
Okay, very good. So basically what she's trying to say, so we have considered that x is my independent variable, y is my dependent variable. So if you take the zero value of x, right? So the at least the value of y should be beta, right? So that's what is called intercept. Okay. And this equation, this line has some slope. That means whether it goes in that direction, whether it goes in that direction, whether it goes very straightforward, right? So that will be determined with the value of beta. Okay. So we have this mathematical formula to estimate this beta naught from beta 1 from the sample population, sample data set. So now come to this meaning. That means what why this equation is written in this manner. Okay. So now we can see that y, if we consider y as a dependent variable, a is your intercept, d is your slope. So what's the meaning of this arrow? Epsilon. What's the meaning of this thing? Can anyone tell me?
So this is the error term because our actual readings will not actually follow the equation always. There will be some error. Like it will
Okay.
not fall on the line of the split or whatever. So that error term.
Okay. So can you give me an example that how this error will come?
So suppose like we have this, we do a regression and we come across a relationship that weight is equal to let's say 40 plus 2
Mhm.
times plus 1.5 height. So
Mhm.
as per that, for a person with height say 100 centimeters, suppose it comes to 80 kgs, but our actual weight is 84. So that 4 will be error.
Okay, very good. So let me tell you more. So ma'am, what ma'am have explained to you, that term is called residue. I will come to that term residue, but let me explain to you this error epsilon term. Okay. So basically, what I'm trying to say here is epsilon means here epsilon is a error term that can be considered as a random. And when something is random and something is variable, so it is called random variable. So let me explain to you. So I think all of you have heard about that. We can only implement linear regression on any two variables if they satisfy the condition of normal. Anyone is aware about this thing? That we can only implement our you can say linear regression model on two variables if they satisfy the condition of normal. Okay, let me explain to you. So basically, in theoretical point of view, but they have explained that. So y is our dependent variable, as I have explained to you that if we consider x as some value of height as 100 centimeters and y value is given as 84. So maybe whatever the value of a and b will take. Okay. So whatever the value of a and b will take, you are not able to get the accurate value of y. The accurate value of y is 80 and we are getting something 81 or 80. So there is some difference appears, right? So this difference will come under when we take the difference of model that we got from the sample observation and the true value of y. So the difference in that case is 4. That is called residual term. But error term is used that in a more broader sense. It shows that this equation is not adequate enough to show the actual value of y. So whatever the thing that is not explained by this model, that comes under error term. So an error term can take any value. It is not a fixed value. It takes +2, -2, and other things. So whatever the difference that will come. So it behaves like a random variable, and it satisfies the condition that it follows normal distribution with mean 0 and variance sigma. Maybe this thing will be more complicated for those students who are not on mathematics background. Let me go to graphical. So what I'm trying to say, so to construct a strong, you can say, or valid linear regression model, we have to cross-check that whether the pattern of error when you plot for all the variables, that means for all the values that we have taken. So let us suppose we have sample of size 50, and we assume that after solving the model, when we plot our error term, right? So it behaves like this normal type of shape curve. Then we can say that it satisfies the assumption model. And I will show you two of our tests, statistics and R programming, and how to do the testing of these things. Okay. So now further, so we have this error term as a random variable that must satisfy this condition that is for normal distribution with mean q and variance sigma square. As already explained, the value of sigma square is not known to us. So we estimate the value of sigma square from the sample observation. Okay, so that is another thing. But now, what I want to emphasize here more, that let us suppose you have constructed or estimated the values of this A and B, then your model will be this one, A hat, B hat plus X. So I think maybe you have seen most of time that you have to estimate this value from the sample observation. There are some mathematical formulas are given also. So I'm not going to explain what those mathematical formulas. My main objective is that after estimating these parameters, so how our equation looks like. So we have now, in spite of y, we have y hat. So y hat is basically a equation that we got after putting the estimates of a hat and b hat. For example, so if height is my independent variable, so I got that 1.1 and some value as 50 plus something. So if y is my weight variable, right? So I can say that if the person height is 0, for example, the person is newborn, then is at least weight is 5 kg. Okay. So height, we are not talking about the height of newborn is something in terms of inches also, but if we, because when we talk about from mathematical point of view, so everything is not valid in real life. So we have to make some assumptions. So if we have to assume that if the person, there is no height, so at least the person has some weight. Although we can't say that the person has no height doesn't mean that the person is not there. So we have to assume something. Okay, so we are assuming that if the person height is something as 2 centimeter or 5 centimeter or 10 centimeter, then how it will impact the value of weight. So we are saying that it will multiply it with 1.1, and then we are adding some minimum weight of each individual corresponding to that, and we will get the value of y. So this value of y that I got, that the value of A I got from the sample observation, the value of B hat I got from the sample observation. That make a statement that is called y hat, estimated value of y. And we will see the difference of y from the value of y that I got from the data, and this value of y hat that I got from the equation. I will take a difference. So that difference is called residual that I already explained. Okay. So we want that because we are saying that epsilon is a random variable and it has normal distribution with 0 mean and variance sigma square, but sigma square is not known to us. So what we do, we want that our residual must satisfy the same characteristic that is the characteristic for the error. Okay, so for example, let's discuss this thing further. Okay, so I have taken 2, 3 observations. So I got some residues 1, 2, 3. So while plotting these residues, so because I have taken 3 observations, so I want that if I construct the you can say bar plots here, I'm taking a histogram here, but it should be bar plot here. So they should behave like it in such a manner that if I fit it over the observation, so the normality assumption should be satisfied. Okay. So after fitting this thing that our assumption of this residue is satisfied, so what is our main requirement? Our main requirement is that we have an assumption, again another assumption, that sigma square that we have assumed, that should be homogeneous for all the observations. Okay. So what's the meaning of homogeneous? The homogeneous means that if we take some observation 1, 2, 3, 4, right? So now I think someone has an assessed Meher sensor. Are you there? Hello. Okay, let me just continue with my discussion. So what I want to say that, so we have 5 observations and we want that for each observation, we assume a constant variance. Okay, this is the main requirement. I will explain graphically also. So let's start with the discussion through example. So I'm going to discuss about first regarding the scatter plot, as already explained to you, that what is scatter plot, in which we draw the points of x and points of y on the both x-axis and y-axis, and then try to see that whether they are linear related or not. So why we can say that they're linear related? Because if we draw some line over this 45-degree line over this point, so most of the points, that means most of the points lie on this line. So we can say that they can be considered as a linear relationship, but it is not equal to +1. So it is lies between 0 to 1, right? But because that is on one side direction, that is a positive side, that is called positive correlation, a positive relationship between these two variables x and y. So there is another example in which you can see that. So here we have this curve that is not a straight line, it is like a concave curve. So we can't able to fit all those points that comes on the lower side of this line. So we can say that that relationship is not linear. The relationship is not linear. In the same manner, if there is any relationship exists between these two variables x and y, that is on decreasing side. Okay, so we can say that the relationship is this one. Okay, it is -1, but it is not more than 0, but lies between -1 to 1, and it is not also equal to -1 correlation coefficient. Okay, so it means most of the points lie on the straight line, but maybe some of the points they do not lie, but they show some negative, opposite relationship between x and y. So again, we see that there's again a curve that again most of the points they do not lie in the straight line, so they behave like some exponentially growth values. So most of the points do not lie in the straight line, so we can say that there is no linear relationship between these two. Hope this idea is clear. Are you with me? Right? Hello. Does anyone has any doubt now? My voice is clear?
Yes, sir, it's clear and no doubt.
Okay, fine. So now you can see that when we say that the relationship between x and y, that is strong enough, when most of the points they are very much close to each other. And while drawing a straight line over these 2 points, so we find that all the points must touch over straight line. Then we can say the relationship is very strong. So when we talk about weak relationship, then there are some points that is very far away from this straight line, And in that case, we can say the relationship is not very strong, right? So in the same manner, this is for positive side, this is for negative side, and this is for again negative side. Although relationship exists, but that is not very strong on the right hand side part, but relationship exists. So here we can see the no relationship in which most of the points are scattered. Okay, so here you can see that we can't fit any straight line on upper side, lower side that covers all the part. That's why it is called no relationship. Or we can't say this scenario as no relationship because it's a straight line, but we want this thing to be at 45 degree, but it's a straight line. Okay, on the vertical side. Okay, so in that scenario, we can say that the relationship is very clear. So I already have explained to you that what's the meaning of correlation coefficient and the range of the correlation coefficient. And what's our main objective? Our main objective is for the mathematical equation. We want to derive the value of R. And if the value of R is -1, we can say the relationship between X and Y that is very negatively correlated to, negatively related to each other, negative linear related to each other. That's why we have value -1. So here in the next example, we can see that again we can create you can say a straight line that shows the negative relationship between these two X and Y, and but it is not very strong because the value is -0.6. It is not -1. And when there is no relationship of this, so we can draw a vertical line that shows that there is no relationship between these two. So now, in the same manner, so if you want to say that the relationship is of positive side, but it's very weak. So in that case, we will use plus 0.0, plus 0.3. So it shows that the relationship is positive, but it is very weak one. So now to check whether we can say this relationship is significantly effective or not. So during the testing of this thing, we have this method that is called testing for correlation coefficient. Okay, so it means that we assume that rho is equal to 0, no correlation exists, rho is not equal to 0. So we have correlation coefficient. So I have explained this formula earlier, R upon square root of 1 minus R square multiplied by n minus 2 to given the parameter here with n minus 2 derivative. Although this formula is not required for you, right? So is there a evidence of relationship between this tree and trunk diameter? Okay, so this is example in which we have one variable as a height and the second one is diameter 1. So we can see that no correlation and correlation exist. So what is main objective? We want to see that rather than the correlation exists between these two variables and no correlation exists between these two variables, and whether it is alpha is 5% or not. So we can see that we already have discussed that if there are 8 observations, the degree is 6. And after putting the values in this mathematical formula, we got 4.68. Now, although we have not very much concerned about that, we have to compare this calculated value with the tabulated value because we can cross check the same thing for the p value also. But if someone is interested that how to proceed further, then one has to see that. So this is my calculated value, and I have to see the tabulated value, and the table value is 2.4469. So how one can get this value? So you have to go to the p-distribution table. Then you have to go to this 6 degree of freedom, and corresponding to 6 degree of freedom, you have to see that what's the value of this 0.025 or 2.5% on two-sided test. So you will get 2.4469, right? And now you can see that 2.4469 is less than 4.68. So it means we are going to reject our null negative. The idea is clear. Should I repeat again? How to make a decision based upon the value of the calculated value. So whatever the calculated value we have derived here, we have to compare this value with the tabulated value. And how to get the tabulated value? We have to go to the distribution table, and we have to go to this degree freedom 6, and corresponding to that we have to see that there will be some columns. This column shows 1 degree, 1%, this shows 10%, this percent, 5%, 2.5%. Then you have to go to 2.5% column, and you have to see which row corresponds to 6 degree freedom, and then select that value. That value will be 2.4469. And now we have to compare this 2.4469 with 4.68. So 4.68 is automatically greater than 2.499. So our value of 4.68 lie on this rejection part, right? If it lies on the rejection part, so it means that we have to reject this null hypothesis that there is no significant correlation exists. So it means there is strong correlation exists between these two variables. And we are not much concerned about that whether it is positive or negative. The main thing that we want to emphasize here is that whether there is significant correlation exists or not. And to cross check whether it is positive or not, we can see from the R value. And if it is coming to +1 or if it is coming close to -1. And based upon that, we can make a decision that there is a positive relationship between these two variables or negative relationship between these two variables. Now, if we got this information that rho is not equal to 0, then we can proceed further to construct a regression equation. So what regression equations tells you that whatever the two variables that we have considered, so one can play the role of dependent variable, one can play the role of independent variable. Okay, not always y is a dependent variable, x can be dependent variable also, y can be independent variable, that depends upon the situation. But generally we fix this notation to represent a dependent or independent variable. Okay, so now I already have explained these things. So what is the role of this regression equation? So now whatever the line we have to draw, earlier it passes to origin, but when we consider this equation a plus b of x, then this line starts at least value of a. So this is the value is called intercept. So whatever the gap we have observed on the x-axis, that is the value of intercept. Similarly, if there is no any gap, that means a value should be 0, and we have this relationship y is equal to bx y. Okay, and whenever we have linear relationship exists between these two variables, and we can see that most of the lines that is close to the straight line. Okay, this is the example in which you can see that positive linear relationship exists can be shown to this graph. Negative linear relationship exists between these two variables can be shown to this graph. And if there is relationship exists between these two variables, but that is not linear, so that can be shown through this graph. That means we are not fitting a straight line, we are fitting some non-linear curve. It can be quadratic, it can be cubic, it can be any other of higher degree, but it is not a straight line. Okay, so in the same manner, so if we draw a vertical line, so it means that the relationship, there is no relationship exists between these two variables y and x. Okay, so hope this thing is also clear to you. So as already explained to you that what is the expression of this y is equal to beta naught plus beta 1 x plus epsilon term. So y is a dependent variable, all of you are very much familiar. So this beta naught represents intercept, this beta 1 represents slope, and x is an independent variable. So this component is called linear because that helps you determine the relationship between x and y. And this component is called random error because that is not known to us in advance. So we have the values of x that is known to us in advance. We can estimate the values of beta naught, beta 1 from the sample of the question, but we do not know what type of difference that can be there after putting the value of beta naught, beta 1 equation, and we have this difference. So that is not known prior to us. That's why we call random error. And it is also called residual in terms when we take the difference of y minus y hat. Okay. First, it is a random variable. When you exactly put the difference of y minus y hat, that is called random error or residual. Okay. So linear regression assumption. So error values are statistically independent. So this is a requirement that our error term they behave independent. That means if you keep changing on the observation, let us suppose in a class I have 50 persons. So I want that to get more accuracy. I want that there is no any connection of one student with the other one. That there should not be any siblings there. Although they are siblings, but we can't say that one height can be uh, predicted from the height of another student. So that is the assumption that they should behave independently. So it may be possible in a house that there are two twins. Okay, some student may, some first twin may be body structure will be different from the other one. Okay, so most of the cases we have observed that they grow equally. So there may be less you can say differences between the twins, but sometimes it is possible that one height is more than other one, some weight is more than other one, right? And there are some cases like siblings. Siblings, they may have different structure also. One can be thin, one can be bulky. So we need this assumption that they behave independently. There should not be any relationship exist between them. And the second assumption I've already explained to you that our error term, while plotting the error, so I need this bell-shaped type of curve. Okay. So this requirement that the distribution of error is normal, that should be satisfied. The fourth assumption is the error has constant variance. So the constant variance means, so whatever the variation we have observed for one, you can say group, if you change the group, there should not be any difference in the variation. For example, I have taken one class, like that is was fourth class of government. Okay. And I have constructed a model, the above model for height and weight. And I want to check that whether my model works for the fourth class primary school students or not. Okay. So whatever the model I put here, so if it works for all the students who are studying in the fourth standard of any school, okay, then that model should perform well for the students also. Agree with me or not? Hello. My point is clear. Hello.
Yes, sir. Yes, sir.
Yes.
Okay, so basically what I'm trying to say, so while constructing a model for one group that is of four standard for government school students, and if I want to fit model for the other students that is from different school, so if my model is good one, then it work well for these two groups. And if there is a problem that this group has less variation, the variation is for this group is 2 and the variation is for this group is 3, then in that case, my model will not work well. So we need this assumption of homogeneous variance, that whatever the variation we have observed for one group, that should be same in the another group also. Otherwise, that you can say the accuracy of the model will reduced. Okay, and whatever the result we got from the model, that is not good enough. Okay. So the underlying relationship between the x and y variable statement, that is very basic criteria, that whenever we plot x and y, so most of the points should lie on the straight line. Here I'm assuming that intercept is 0, but if I assume that intercept is non-zero, then it starts from here and go up to the number of observations. Okay. So I think till now, most of the students, they are very much familiar with this term, that what is going on. So here you can see that this is one value of xi, this is one value of y. So we put dots. This value shows the combination of x and y values. I think this is clear. This is your intercept, that is at least value of y, that is beta naught. So this shows, this black dot shows the values of pairs of x and y values. So this is my regression equation. Okay. So what we are concluding from this regression equation, now you can understand it more better manner. So the equation that I have constructed based upon the observation random sample that I have with me, or observation that is with me, I have constructed the straight line, this line, right? But the actual value, the combination lies here, so there must be some gap in between the straight line and this point. So this gap is called random error, because this thing is not explained by my equation. That is, you can say, remain unexplained. Okay. This is the actual value of y, this is the predicted value of y. So this gap is called, that is not explained by regression equation. So if we have such gap that is not explained, that comes in the random error. Okay, and the slope is already clear to you. The direction of the line, how it is steep or the not steep, that can be seen from the slope, and the slope can be determined through this beta line. Okay. So now you can see that while estimating the values, so we replace the estimated value of beta naught with b naught symbol, and estimate of beta 1 hat with beta small b1. So whatever the value we got from the sample observation, we are putting this value here, and we got value of yi, and we are saying that it's a estimated value of y, not a true value of y. Okay. So this equation I got from the sample, and this value of y I got actually from the data set. The difference is clear. This is the original value of y that I have with me as the initial stage. This value of y hat I got after estimating the value of beta naught and beta 1. And I'm putting it here. I will construct the equation. And after that, I got value of y hat. That is a predicted value of y. So if the value of y and y hat, they are very much close to each other. So in that case, your residue will be close to 0. Okay. That means we have put such equation that explain, that means that cover all the points. So if this point is here, for example, and there is no any other point that is far away from the straight line, then this error term will be close to 0 in that case. And corresponding to that, we can say that we have constructed such an equation that is very efficient enough to explain all those variations that is present in the dataset very well. Okay. So I'm not going to explain that how to estimate the values of beta naught, beta 1. These are the mathematical things, and that derivation is not required for you because whenever we use any software, so they have done all these derivation, but we must be able to understand that what's the meaning of these terms, and we already have covered these terms, right? So now that means after getting the value of y hat, then I'm going to tell me whether my job is over or still I have to do more lot of things. Hello.
Sir, I think we'll have to test the significance. I mean, the error term, whether the residual is just having a normal distribution.
Okay. Any other thing I have to do?
So we'll have to test the significance of it. I am not aware how, but
Significance of what? Beta not beta 1 or something else?
so the I don't know, sir.
Okay, no issue. Thank you for the response. At least you have you have participated at least. So basically, after that, we will test these assumptions also. So this part is not explained when you search anything on the internet. So this part is remain untouched. So I want to emphasize it. So the job is not over. So what we have done, we have constructed equation y hat. So now the job is that we have to check whether if you change the data, if you want to implement this model for the another data set, whether the intercept is very important in your model or not, or the beta 1, that is the slope, that is very important or not. If the beta naught and beta 1, they do not reject it. That means we are accepting this thing, right? So it means that, so we have constructed a model that is very poor enough, because if beta naught is not significant, beta 1 is not significant. So it means we have conclude that there is no relationship between y and x. Okay, so this is again another criteria to cross check whatever the assumptions that we have considered earlier, that is validated or not. So basically, these tests are helpful to make a relationship between the assumptions or whatever the criteria that we have assumed, that based upon that we will conclude further. Okay, so now you can see that we have estimated the values of beta 1 and beta naught. So let's take one example for more convenience. So a real estate agent wishes to examine the relationship between the selling price of a home and its size. So we know that the price is a dependent variable and independent variable is square feet, because when we have more square feet, the price will increase. So they have provided this information, the price of the house here, and this square feet information is given here. So after putting the value in the equation, okay, I got this thing. So here you can see that this is my beta naught, this is my beta 1. So this is my house estimated value. If I want to see that how much deviation I have observed from my house from the this true value of y, so then I have to derive this thing that is called residual. Although this thing is not explained here, but we can cross check it here, that if we take square feet as something like they have taken the square feet as Here is not explained, but let me take another example. So let us suppose we have taken this square root as 1400. Okay, and after putting this value of 1400 in this expression, so what value of household I get? If I get a value of household close to this 245 and $10,000 $1,000, okay, then I can say that my model is very good enough that can explain, that can give me the exact value or close to the exact value that I got from the my observation, or you can say I got from the field curve. Okay, and if there is a large deviation is there, then this model behave is do not work well. Okay, so now here you can see further that our job will not stop, because our main thing is we want to see that whatever the total variation that is present in the data, that is explained by the model or not. So if the total variation is explained by the model R, that the regression equation that we have constructed above, then this sum of square of error should be small. Should I repeat again what I'm trying to say? So let us suppose if I got total variation as 14 and my regression equation explained, well, variation among the top 14 variation, then this sum of square of error should be 2. So if our sum of square of error is 2, then I can say that my model is very efficient enough that explains as much as variation possible in the data. If this sum of square of error is 12 and the sum of square regression equation is 2, then my model is very poor enough that is not able to explain the whole variation present in the data. Maybe some of you have a question in your mind. What is this variation? Is there any question that what is variation? What do you mean by variation? I use a lot variation. So what do you mean by variation? Can anybody explain it? And why we need this thing, that why this variation is very important? Why we derive total sum of square of total sum of square of error, sum of square of regression? I think this thing is very new to me, because if someone has used Excel, some of us use some other tools, so they are more concerned about whether what is the value of beta naught, this beta one, or sometimes they can cross check whether beta naught is significant or not, beta one is significant or not, or whether our model satisfies the assumptions or not. But why we are discussing a lot about variation? So for a simple understanding, so as I already explained to you, that when we have most of the points close to this equation, so the y bar, overall y bar is somewhere here. Are you getting my point? What is y bar? The average value, and when we have some average value that can be determined by taking that what type of observations we have. So for example, if I very observation that they are very close to each other, then the y bar is such a point that can be considered very close to each other. If we have very such type of observations that they are very far away from each other, although those observation has an effect by determining the value of mean, but the mean should not be close to the extreme value. It should be close to the value that comes in the mid, right? So in that case, so if our y observation is very far away from the mean value, that means there is a lot of variation among the observations. Now the idea is clear, and variation can be determined by taking the difference of each observation from its mean and take the square. Okay, so when you're taking the square, but this for all the observation, this, and we have completed all the observation n, this is called total sum of square. Why it is called total sum of square? We are taking total sum and square. This is sum and then take the difference of square. Okay, so this is the whole variation that is present in the data. So we can say that the sum of square regression, the equation that we have prepared, if that equation cover all those points very well, so how much variation that we have observed in the total sum of square, how much variation explained by this sum of square regression? If it is able to explain 80% of the whole variation, and remaining is sum of square of error that is not explained by anyone. That is 20%. So we can say that our model is 80% efficient enough to explain the variation present with it. And that can be determined through a value that is called R square. That's called coefficient determination. How many of you have heard about this term coefficient determination? Any idea? So is there anyone who have heard about the term coefficient determination or not? Okay. Till now,
Yes, sir. Small r square by 1 minus r square, I think.
no. So you are participating, that is very good thing to understand, but let me make it clear. So we know that what is the formula for R, that is R coefficient coefficient. So when you take the square of R, small r, it will be called capital R square and coefficient determination. So I will prove my point later when we do the coding in R. So you have seen that the value of small r lies in the range of -1 to 1, right? So if you take the square of any negative value, it will again become a positive value. So for example, in the previous case, I got that the R is close to 90%. That means 0.90 on the positive side. So when I take a square of this thing, so it is 81, 0.81 or 81%. Right. So it means that my model explains 80% of the variation. 81% of total variation that is present in the data. Okay, total variation is there that we have already have discussed above or below this. Somewhere I have it up. Equation. This thing. The total variation is 100%. So my model explains 81% of the variation. So remaining one is 19% that is not explained by the model. That is explained by the error term, or that is unexplained. You can see. Okay, so from the value of R square, that helps you that how much variation is explained by the model. So now going further, so now come to this part that I want to explain to you. So how this thing will work? So you have seen that this is the value of xi, this is the value of y, and we put this point. That is the combination of y and xi value. So we have constructed a mean line, that is a y bar here. Okay, so now you can see that when we have constructed this y bar, and this is my regression equation that is represented by y hat. So while constructing a line through all these segments, so you can see that, so we start from here, go till here, because y bar is the mean, SSR is the variation that is explained by the regression equation. SST is the total variation that starts from here and go till the stage. And the sum of error that is not explained by the model, because our model has capacity to go till this state. It doesn't have the capacity to go till this state. So that is unexplained. So in the same manner, we derive this thing for all the combinations of YA and XI, right? And we accumulate it together, and whatever the value of R square I got, that helps me to make a decision that how much variation explained by the model. And if R square is equal to 1, I can say that my model is perfectly linear weighted. That means my model is very good enough. So that explains the variation between X and Y. Okay, although in real life, we do not want R square is equal to 1. Can anybody tell me what's the reason behind it? In real life, we do not want that R square should be equal to 1, or R square should be not equal to 100%. What's the reason? Okay, so can you tell me that? So are you able to construct any model in your life, or when if you take multiple, you can say birth? Okay, so are you able to construct such a model that can tells you that if the height of the person is this one, the weight should be this one? Are you able to understand what I'm trying to say? Are you able to construct any linear regression model that tells you that if the height of the person is this one, the weight should be exactly equal to this thing? It should not be go beyond this thing. Can we do that or not?
No, sir. Usually, sir, because the dependent variable depends on a lot of other factors also.
Yes, so that's why we will talk to because here we are taking only the example of simple regression model. So we are not considering other factors. We are saying that there is only one factor that can determine the weight of the person, that is height. But we can't say exactly that if the height of the person is something, then the weight should be this equal to this. There must be some variation between the height and weight for different persons. So you have seen that in real life also the height of two persons are same, but they may be variation in the weight. So how our models would know if we say that R square is equal to one? Got my point? So I'm coming to that scenario also when we will talk about multiple regression model in which we do not take one independent variable, we will take multiple independent variables. Okay, and then we again have to satisfy some assumption. That is different scenario. But for till now, I'm talking about simple regression model in which I'm saying that one independent variable is there, one dependent variable is there, but still we are not able to construct any model that is 100% accurate. Okay, hope my point is clear to all of you. Okay, so what we need, so in that case, we want that our R square should lie within some range that is 0.70 to 0.95. Okay, so that in such cases, if some model R square is 0.70 to 0.8, we say that the model is acceptable. And if it is lying in the range of 0.80 to 0.90, that is good one. And 0.90 to 0.95, that is excellent. But if it is more than 0.95 to 1, so there is some suspicious thing will happen, right? So we have to think that whether there is some issue of overfitting is going on, whether the person has done some you can say uh, modification in the data. Okay, so there are a lot of things one can trigger. That means there is a lot of things that comes to the mind of the person. So now I'm coming directly to the things that I want to explain to you. So that is after that, after doing our exercise, we have to now come to the testing of the regression coefficients, that is beta 1 and beta naught. And for your understanding, it again follow t-distribution. And from when you do the coding, okay, you will have the output in which you have to concern about the p-value. Okay, so this example is run in Excel. Okay, so you can see that while execute this output in Excel, so you will get the coefficients first, you will get the coefficient for intercept, you will get the coefficient for scale fit, then you will get the standard error term, you will get the t-test, and you will get the p-value. Here, for your understanding, I am more focusing on the p-value because it is very easy for you to understand the concept of p-value. So now you can see that the intercepted p-value is greater than 0.05 and I'm assuming the alpha value as 5%, right? So, and here scale fit is coming less than 0.05. So in that scenario, which condition I have to follow? Whether this is true or whether this is true. My question is clear? Hello? Hello? Should I repeat my question?
Sir,
Or it is fine?
please,
Well,
one.
what I'm trying to say, so from the p-values, so which one of these two equations, which one is true or false? Whether the
Sir,
statement is true or
the first one where the p-value is 0.32.
okay. So this equation is true, right? So it means we can say that if beta naught that is not significant. That so here, what is the meaning of significance? So it says that so we have this assumption that if the house do not have any square feet, still the value is 98. That is not a value statement, right? So the next statement says that the coefficient of square feet, that is beta 1, that is significant. That means beta 1 play very important role in our model. So we should not consider as a zero, should not be not equal to zero. This is the main thing. Okay. Okay. So again, one can also derive the lower and upper confidence interval, like I have already discussed yesterday, that one can derive the lower and upper confidence interval, and based on this lower and upper confidence, you can also make your decision. For example, in the first confidence interval, the zero value lies, so beta 0 is equal to 0. That condition is satisfied from the confidence interval. So we can say that this hypothesis is correct one for beta naught, and this hypothesis for beta 1 is not equal to 0, that is correct one, because it doesn't hold the value of 0. Right? So I already explained these things to you. I think we should go directly to our programming because we have limited time. So let's start with this. Right? So I already discussed with you that what are topics we are going to cover. One is called correlation analysis, simple regression model. And now I will also give you some brief understanding about multiple regression model. Okay, then we will do some assumption tests that already explained to you. So the concept of correlation is, I think, clear to all of you. So in R programming, we have a function or syntax that is used for determining the correlation. That is a cor.test. And we have taken a inbuilt data set that is called empty cars. I think if some of you have some prior experience of using R, then must know that there are some inbuilt data sets. So empty car is one of the inbuilt data set in which there are some variables. Okay, that is called mileage per gallon. This HP means horsepower. So basically, empty car is a data set that consists of some variables that helps you to give an information regarding the price of the car based upon the features like mileage per gallon. Because in America, gallon word is used. It is not like mileage per petrol. So they have it. So mileage per liter. They have a term that is called mileage per gallon. And HP means horsepower. And then we have gearbox. If you explore this data set in our programming, then we have the price of the car, the make of the car, and model of the car. So there are other variables also available in the data set that is called empty cars. So I have taken one combination. That means I want to see that whether there is any strong linear relationship exists between mileage per gallon or horsepower. And I have used Pearson regression, Pearson correlation coefficient. So can anyone can tell me whether they have heard about Spearman correlation coefficient or not? And what's the difference between these two terms?
Yes, sir.
Okay, so can you give me some brief layman terms in the explanation of these two terms? Spearman correlation coefficient and Pearson correlation coefficient. Okay, let me explain to you. Okay, so if Pearson correlation coefficient will be used when we have quantitative data set. Quantitative. Quantitative means, so we have these variables, mileage per gallon, horsepower per gallon, that can be quantified. Okay, quantified from the machinery of the cars. So when we have such type of variables that take qualitative value. For example, I want to assign some ratings to the performance of a student. So I can scale it from 1 to 10, right? So now here 1 and 2, they are not mathematically equivalent. It means they are not satisfying the property of mathematics. For example, if in mathematics we assign something to that is double of 1, but while it's giving some scaling from 1 to 10. So if someone's scale is 10, someone's scale is 1, we can't say that the person is 10 times better than the one and the person whose value is 1. It is just a way to make some difference between the performances, and we can assign some values that is just for the representation purpose. Are you agree with me? This thing is clear or not? Hello. Okay. So in that scenario, if we have two variables, one is called performance, second one is called presentation or communication skill. So in the same manner, we can give some rating from 1 to 10. In both these cases, the values that we assign, those are called ranks. Okay. So when we want to derive correlation among the ranking observation, then we go with the Spearman rank correlation coefficient. Okay. Otherwise, we will go with the Pearson correlation coefficient. And from the correlation coefficient, what we get? So we get that p value as less than 0.05. This is the first thing we get here. And we get 95 confidence interval as this thing that will consist of negative values. So this is a negative correlation exists between these two variables. And the correlation, the exact correlation coefficient is minus 0.77. So it means that so when we have higher horsepower, then the mileage will decrease. That thing is valid. So for example, if we are using 1000 cc engine car, so if we increase engine capacity to 2000 cc engine, then automatically the mileage will decrease. So this thing is validated from here, and that is already proved from the p-value that these two variables there are strongly linearly related to each other, and the correlation coefficient is again close to -1, right? So we have added to both assumptions that both the things that we have discussed earlier. So again, we want to do some other example in which we want to make see the correlation between mileage per gallon with the weight of the car. So again, we derive the same thing. They are coming significant, and the correlation coefficient is very strongly negative. So in the same manner, so I have taken examples from different data set that is inbuilt in our programming. So there's no requirement to go here and there. So when you type this data set, that is iris. So that will have 4 variables. The variable names are sepal length, petal length, the type of the category, and the weight of this sepal height and petal height. So what is the meaning of what we have in this data set? Let me tell you the brief. So basically, in this iris data set, we are talking about the length and width of the leaves, or sorry, leaves of the plant. Okay, so, and we want to make a connection that whether the length and width of any plant leaves they are related to each other or not, and we want to test that the sepal length and petal length they are related or not. So for that, we have conducted this correlation coefficient, and we again got positive relationship between them, and that is coming significant. So now we can easily see that the interpretation is very easy for you because we have covered the theory theoretically first, and without theoretically theoretical knowledge of things, you can't interpret the result that is given. And what is our null hypothesis? That is rho is equal to 0, and rho alternative one is rho is not equal to 0. And what rho means that there is no relationship exists. Rho is equal to 0 means there is no relationship exists between this sepal length and petal length, and rho is not equal to 0 means that there is strong linear relationship exists between these two variables, and so on. Okay, I have put more further examples. You can do it also. So let me take one example of. I think I have kept it of the Spearman. Okay, I forget it. Let me come to the simple indication model. So now to implement simple indication model is very easy now. Okay, because it is very easy to write down the code. You have to use this function ln linear models, put a bracket, mpg is a dependent variable, and this weight is a independent variable. And we have taken data from empty cars, so that's why data is written as data is equal to empty cars. So when you execute this code, and so one thing you have to keep in mind that you directly have to copy or write down this code in your R console also, you will get the same output. So there is nothing to worry about. So if you write down this code directly in your R console or R script, you can get the same output. So from the output, what we will get? First, we will get the summary of the data. What is the minimum value? What is the first quartile value? The median value, the third quartile value, maximum value. And after that, you can see that we got the coefficients. So this is the coefficient for intercept, That means the value of intercept, and this is the coefficient of weight. So we got that both are coming significantly because the value is less than 0.05, and there is nothing to see cross-check if the asterisk symbol are multiplied. That means they are written simultaneously corresponding to this coefficient. That means automatically it is less than 0.05. Okay. So now the interesting thing I want to explain. The interesting thing is that is this thing, multiple R square. So here the value is coming as 75.28%. So it shows that whatever the equation that we have constructed for determining the value of mileage per gallon based upon independent variable as WT. So that explains 75% of total variation. Okay, so we can say that this model is good enough, and to cross check whether our overall model is good or not. So we want this p-value to be less than 0.05. Okay, so that is again satisfy some conditions. So now we have to test the assumptions. So whether our model satisfies the assumptions or not. So in that case, we have to execute this code, and this code, the meaning of this first line says that I am constructing a box in which I am putting this 2x2 matrices, and I want that all my plots that I want to construct that appears like this 2x2 matrices. So you can see that after execution of this code, you will get 4 plots in terms of matrices. In the first plot is shown as the first cell observation, and second plot shows as the first row, second column observation, and so on. So now we are going to interpret this thing. Okay, so basically what is going on here? So these are my fitted values. Fitted values for the values of y hat, and these are the residuals. Residual already explained to you the value difference of y minus y hat. So now you can see that. So here, by putting these, you can say, putting these points, there is most of the points that lie outside this limit. So what is the requirement for our model? We want that residual should behave randomly. There should not be any pattern. So that pattern is not observed here. So we can say that our model is good enough. In a similar manner, to test the assumption of normality, we have another way to test the assumption of normality satisfied or not. That is called normal QQ plot. So while plotting all the observations quantile here on the straight line, if all the points, these are the points, this is straight line. If all the points lie on this straight line, then we can say that assumption normality is satisfied. Okay, the same manner, we can test that whether there's any relationship between fitted value and the standard residual. So that can be seen that can't be there because these observations are scattered enough. So we can say that there is no relationship exists between the fitted value and the standard residual. That is again a requirement because we have assumed that our IID, this error term should behave independently. So this assumption is also satisfied. Okay, so in this manner, what we have concluded that whatever the model that we have assumed for the fitting of MPG, okay, we have considered WT as an independent variable, multiplying with some coefficients and adding the intercept term. So that model is good enough to explain the values of MPG. So as already explained to you, then in literature there are various tests available. Okay, to test the normality assumption. Okay, the one test is called Shapiro test, Shapiro-Wills test. And what this test tells you that the assumption of the null hypothesis that the data set is from normal distribution. Without satisfying this assumption, we can't say that our model is good enough. Okay, and alternative one is data is not. Okay, so here you can see that p-value is greater than 0.05. Okay, so here you can see that we do not reject the null hypothesis. Okay, so in that case, we can say that our assumption already is satisfied. So again, there is another assumption that was sigma square should be homogeneous. To test this assumption, we have a test that is for Bush packet test, and the syntax is BP test. So when I execute this test, so I got that p-value is greater than 0.05. So here our null hypothesis that sigma square is constant or homogeneous. And alternative one is sigma square is not constant or not homogeneous. So here our assumption is satisfied because p-value is greater than 0.05. So this assumption is also satisfied. So now we can say that whatever the model that we have constructed for the fitting of mileage per gallon, considering WT as a dependent variable, that can be used further. That means if you change the data, if you take the data for other companies, okay, that also satisfies this requirement. Okay, any question till now?
Excuse me, sir.
Yes, ma'am.
Sir, in some of the previous examples, you were showing the value, p-value was really, really low, like it was 10 to the power minus 16 and all. So there the null hypothesis was rejected, is it?
Yes, yes.
Okay.
So basically, you have to understand what I'm taking as a null hypothesis. This is very important thing. So we do not always want that p should be less than 0.0. Okay.
Oh.
So here you can see that the assumption says that what is our assumption? First assumption that normality assumption is that it should be there.
So yes, sir, normality for the residual.
Yeah, residual. So we have tested for the residual normality assumption. It is already written residuals, RESID, residuals, right? Are you able to understand what I have just explained?
Yes, sir. Yes, yes.
Okay, give me 1 minute. I have to just do some. Just give me 1 minute. Okay, so now we can proceed further. Like you can take multiple examples by considering MPG as a dependent variable and HP as an independent variable and so on. So now from the further analysis, we got the same thing that our coefficients and intercept are coming significant, and we got now R square as 60%. In spite of R square earlier, now it is coming as 60%. So can you tell me what you have concluded from this example in the previous one?
So this means that the model only explains 60% of the variation.
Variation. Yeah. So it means that if we take HP only as an independent variable, so we are not able, that means we are not able to get good results, right? So it means that, so WT play very important role as compared to the, you can say HP. So again, we have tested assumption of normality. So again, it is coming at, earlier it was coming at greater than 0.05, now it is coming less than 0.05. So it means the residuals of the model that doesn't satisfy the condition of normality. So we can't proceed further. So most of the students, what they do, or most of the participants, they have constructed both in this stage, and they found that our model is coming significant. We got R square as this one, but they have not checked whether our model satisfies the assumptions of normality, whether they satisfy the assumption of constant variance or not. So this is the difference that I want to discuss in today's session, that we have to also do these things, practices, then only we can generalize the results for other data set. Okay. So now I'm taking further for multiple unification model. Let me see where I've kept that example. Yeah. So now we have seen that when we have taken WT only, we got 75.28% R square. And when we have taken HP only, we got 60%. And again with MP as is HP, we found that our normative junction is not satisfied. So now let us suppose if we take it together. So how much improvement that this adding a new variable will bring in improving the value parse? Okay, so we have done the same thing again, and we found that our intercept is significant, our WT significant, HP significant, so on. Right. So now we have seen that our model has improved from 75.28 to
Excuse
80.
me, sir.
Yes.
Sir, I have a doubt here. Will you please explain, sir, normally when P is greater than 0.05, we say that, that's significant. Why, is it how have we constructed the hypothesis
Okay.
for these? Yeah.
So basically, I think there is some confusion here. So what I have explained here that so these are my null hypotheses, right? For beta naught, beta 1, and beta 2. Right. So we have seen that we are rejecting all three hypotheses. That means alternative one is true.
Oh, yes.
Right.
Okay, sir, got it.
So now our job doesn't end here because now we have another assumption. That assumption is called testing of multicollinearity. How many of you have heard about the term multicollinearity? Okay, so whenever we consider more than one independent variable on the right hand side part, we also have to test that whether these two variables they are actually independent or we are assuming they are independent. Okay, so we have to test the assumption that whether they are independent or not. For that, we have to go or implement this test that is called VIF, variance inflation factor. And if it is value is more than 10, in some other books it is written as greater than 5 also, but it is generally considered as more than 10, then we got the information that they are related to each other and we can't proceed further. Either we have to take this variable alone or we have to take this variable alone. But here we find that both value is less than 10 or less than 5. So we can proceed further in that direction. And we can also cross-check the further assumptions like testing the normality, testing of Shapiro dot will test and other things. Okay. So in the same manner, we can proceed with another example in which we can take WT with the QSEC, another variable name. And we have seen that earlier we got 82.68%, now we got 82.64% of R square. Right. And again, we will test the assumption of multipolarity. And there are various examples I have kept it for you for your better understanding, in which some of the times one assumption is not satisfied. Then how to proceed further. So this is the main idea, that keeping all those examples here. Okay, and for understanding also. Let me see where now see the testing of assumptions where I have kept it. Testing of yeah. Okay. So now basically the assumptions have been tested here only and it is not kept separately. But now our main objective is after putting the model, we want to give the forecasted value. I think this idea is clear what I am saying here. So we have put a model M1 earlier in which we have kept WT as a dependent variable and our independent variable and dependent variable is miles per gallon. Okay, so now what we want to do is we want to give some initial values of WT and want to get the predicted value for M. So when we use this the previous model, we got this prediction values. If you use this function predict and put the same thing like this model here that we have used earlier, that we have depicted earlier, and we have prepared this data frame in which we have put the value of WT as these things. So now we have discussed that after fitting the model, our main objective is to provide the forecasted value for each model that we have discussed about. Okay. Yeah. So any doubt you have till now in any segment, one can ask. I think I have covered your queries, whatever the doubts, whatever things that you have missed while putting the simple regression model. Someone has asked me yesterday that so whether you will cover cross-sectional and longitudinal study. So let me tell you the difference between these two first. So cross-sectional means, like the example that we have discussed just now, that we are covering different observations at a single time. For example, if I'm collecting the information from the class, okay, that consists of 50 students, 100 students, and their height and weight. Okay, or we can think about that I am considering example in which I'm taking 50 cars or different weight, but at the same time. So that is example of cross section. Longitudinal studies or time series studies are those studies in which I kept only one variable. Like if I take an example that I want to make a model to determine the value of any company stock tomorrow. So that will be called time series model, in which we take one variable at a time and we keep on observing the value of that variable over different times. For example, if I want to construct a model, then I will take the last 10 years values of the same company stock price to see whether how much variation is observed throughout the 10 years time period, throughout the 5 years time period, and so on. So those models are called time series. And in the literature, there are various models like autoregressive, moving average. Although this is not part of today's session, but for your understanding, because someone has asked me, so I'm giving these models names: ARIMA model and MA model. So these are the models that will be used for the putting of such cases in which we consider only one variable X, and we try to say track the performance of this variable at the time. And I think someone has there's any other question that I have not entertained till now. I try to limitation of correlation coefficient. What are the limitations of correlation coefficient multiplicity analysis, and how to remove this problem? So basically, correlation of coefficient that is an initial state that helps you to check whether a strong relationship exists between the two variables or not. Okay, and in the multiplicity, that we have various methods like how to remove the problem multiplicity. As already explained to you that when we use VIF method, and if it is any values greater than 10 or 5, we remove that variable from the study and then try to again put the model. And dummy variable regression model is entirely different thing, in which we have one independent variable that consists of some categories, and we will assign some binary numbers to the levels. And that analysis can be done, but that is not part of today's session. So if you want to study more, I can refer you one book that is by the Motor Gujarati. Or if you want to emphasize more on emphasize on using some software that is dedicated to combinatorics, that is called eViews. And if you can see how they use the concept of dummy variable in the model, and you will get the output, and the interpretation will be same. Our main objective is to see whether those variables, independent variables or dummy variables, that they very important to significant to determine the value Y or not. Okay, any other question from the audience? Arun Kumar Mandal, whether your queries resolved? Hello. Are you there?
Sir, there are two questions in the chat box.
Okay. So I'm not able to see those questions. Where are those? I've explained these questions.
Okay.
Any other question from the audience?
Sir, I wanted to ask one question. For my research, like when I'm looking at other research papers, there's some which have done used because I'm doing on performance of mutual funds, so there is this time series data. So in a lot of papers, they've used this ARIMA modeling and sometimes
So
arch, branch, etc.
that's
So
why I'll explain to you that these are the basic model that is used for the time series data.
yes, sir. So my question only is this, that see, sir, I don't understand the mathematics behind it, like the whole calculations, the differential equations which run in 2 pages. So without understanding that, like having a basic idea of what that test is and what the results, if I can interpret that, can I use that? Because using this R programming and all
So basically,
for my
when we use time series, we have to done entirely different study because those things are entirely different from multi-regression.
okay,
So they have different assumptions, right? And they have different tests.
okay,
Okay. So it is better if you just read the things and what are tests are there and whether you must be able to understand what the hypothesis that they have framed for each test. Like we have seen that some of the tests we want our hypothesis should not be rejected and some of the hypothesis we want should be rejected. So that thing must be clear in your mind. It is not required that you have to go for each mathematical things because that is not nowadays there because we are using softwares only, right? So it is better to have the, I can say, some theoretical knowledge of the concept.
Mhm.
Okay, that is very important because otherwise, so I think no one of you have cross-checked the assumption of normality. Maybe we have used this multiple regression model number of times. Okay, and we have not tested the assumption of homogeneity of variance. So I have seen a lot of publications that just implemented, they have just fitted multiple regression model without testing the assumption of multiple method.
Mhm.
Okay.
So, can you possibly tell us stepwise when we are like, trying to determine this relationship between two variables? What should be the steps? How should we just, we should go about?
So basically you have to start from a scatter plot. From the scatter plot, you can see that whether how much scatterness is there, whether we can put a straight line that can be that can cover all the points. From that, you can see that the linear relationship is there. If there a scatter plot doesn't cover, if it's a straight line doesn't cover all the points, then you can got an idea that the linear model will not work in that scenario. You have to go for non-linear models.
Hello.
Yes.
Oh.
Hello. Someone is asking. Mihir Chan said, can you mute that person?
Any more question, please, dear participant?
And give me your feedback whether you like the session because live is on chat box only because I try my best to not give you a lot of mathematical things, but try to give the glimpse of things that is required for your understanding. I just want to know whether my objective is fulfilled or not.
Sir, I found the session very helpful. I could understand a lot of things which I earlier could not understand on reading the research papers, like, what is happening, how to interpret it, and why those uh, other tests, like you talked about the Shapiro.
Shapiro-Wills test and
Yeah. So, like, I learned quite a bit. Sir. Thank you so much.
Okay, thank you. Thank you. Yes.
One technical question I would like to know, how does temperature affect the reliability of correlation?
Sorry, I'm not getting your voice.
Yes, yes.
Arun Kumar ji, your voice is not clear.
Actually, I would like to know to what extent sample size affect the reliability of correlation.
Sample size affect the reliability of the
Correlation.
Reliability is no word in correlation. We talk about copy, that means how much strong linear relationship exists between the variables. That's the main thing that we can observe from this correlation coefficient. So I'm not able to understand the meaning of reliability that is not emphasized here. it is there that when we have large sample size, we will get more accurate information about the linear relationship between the variables. But I'm not able to understand the concept why we are using word reliability. Reliability word is something different. Here we can only say that our result will be more accurate when we have large sample size. Hello. Hello, can you hear me?
Any more question? Any more question or feedback about these two days session?
Hello, I'm
Hello.
audible, sir.
Yes, sir, audible.
One technical question: why we consider parameter as fixed but statistics as variable?
Sir, your voice is not clear.
Sir, can you please text me in the chat box?
Yes, sir.
Please text. Any other participant, please? Dr. Rina, Dr. Harmanpreet Singh, Sonia ma'am.
I check, sir.
Sir, please check the question in the chat box.
So there is no words of statistics. Statistics are there. Statistic, right? So parameter are fixed because we determine their values. Okay. And we assume random variable corresponding to error term. That means we have assumed error as a random variable. And the function that we got, that means what are the function we use to check the function, that means testing the assumption, that is called test statistic. Okay. So there are some models that also consider parameters as variable. So there is no fixed criteria that we always has to keep parameter fixed. Like ma'am has explained one model like ArchGarch. Okay, so there are some other models like BARCH. So they have considered parameter as a variable also. So I'm talking about the things that we have covered today. So in today's session, we have covered multiple linear regression model in which we have considered both parameter fixed. Okay. So I think we should stick to today's session because if I'm going to explain the things that is out of today's talk, that will be not able to understand other participants what we are discussing. My voice is not clear. Is it clear now?
Sir, it is clear.
Okay, thank you.
Okay, thank you. I think all the questions has been taken and discussed very clearly. And still, if the participant have any issue or any question in the near future, you can contact us and we will try to help you in any way. And I now I request to other participant to please open your webcam for having the group screenshot. Yes, thank you. Thank you to all. Again, I am request to all the participant to open the webcam. Also, I have shared today's feedback form in the chat box. You can access from that place and submit the same. Dear Professor, thank you for your valuable time.
Thank you, sir.
And on the behalf of the organizing team, I extend my sincere gratitude to Dr. Harmanpreet Singh Kapoor for today's enlightening session on inferential statistics. Your clear explanation of correlation analysis, simple and multiple regression, and their applications in business forecasting using R have truly added great value to our learning. The practical approach you brought made these technical concepts much easier to grasp. I also wish to thank to all the participants for their active engagement and enthusiasm, which made the session even more interactive. We look forward to apply this insight in our research and professional work. Thank you once again for your time and efforts in guiding us today's dear professor. And I hope that all the content which are printed in the two sessions we will provide you, and the recording also will be there, so that in the near future you can do some practice, and all the sessions which we have organized this entire workshop will be valuable and informative to all the participants only if we are trying to apply these tools, these methods and programming. Only then this will be very helpful. Otherwise, we have only the 10 days or 2 days certificate, but valuable only if when we will try to apply application in our classroom as well as for the research purpose. So I hope that we all will try and learn these tools for our learning as well as for teaching. Thank you to all the participants once again, and thank you, dear professor. Thank you to all. Tomorrow we will resume the meeting at the same time.